So last time we looked at eclipsed versus staggered conformations. This time we're going to look at the relative energy of those different conformations. And at the end, we'll look at a couple of reasons why we might want to do this. But for now, the main reason is simply to explain the motion that we see when we look at this ethane molecule. And you can see as it kind of moves, as it kind of wobbles back and forth here, is that it's spending most of its time in this staggered conformation, kind of in this area of the staggered conformation. And then it really just tries to skip by the eclipse conformation. And so we can explain that behavior through talking about energy. So I'm going to show you a kind of an incomplete diagram here. This is going to be an energy diagram in a little bit. Before we get to looking at the energy part of it, there is, notice the Newman projections where we go from an eclipse conformation to a staggered conformation to an eclipse conformation to staggered to eclipse to staggered to eclipse to staggered. And one of the things to think about when we think about energy is what high energy is and what lower energy is. And so things that are high energy are not as stable, more likely to change, where you don't want to stay in a high energy conformation or position for very long. It's like climbing up on top of a ladder. You don't want to stay there for very long. You're going to come back down. So same thing with this eclipse conformation, and we saw that in the video too, right? Where the molecule just didn't spend much time in the eclipse conformation. And so down at the bottom, lower down, this is the lower energy, more stable, and less likely to change conformation. And that's that staggered conformation. And, we can rationalize that with molecular orbitals as well. The lower energy, the staggered conformation, has some stability due to orbital overlap between some bonding and anti-bonding orbitals. And of course, it's not eclipsed, and so that's good too. The electron clouds are far apart. And so if we want to think about sort of the relative energy, if we drew a line, it would look like a little sine graph. So let's look at that. So the energy is low, it goes up to eclipse, down to staggered, up to eclipse, down to staggered, up to eclipse, down to staggered. And so we can actually measure that by measuring the relative populations of these two species. And when we do that, we get 12 kilojoules per mole difference. Unit of energy that we're using is kilojoules per mole. And so we can what we do is we say for each of those hydrogens that's overlapping, it contributes 4 kilojoules per mole to that potential energy, to that higher potential energy. And so there's 3 of them, and so 3 times 4 is 12, and that's why we get this 12 kilojoules per mole. That eclipsing interaction is called torsional strain, as you can see here. Now, if we look at a more complicated molecule, butane, you think for a moment what might be the most or the highest energy conformation of butane and what might be the lowest. And so let's look at the highest first. Okay, so that's where the methyl groups are eclipsing each other. Those are the largest groups, and you really just get those hydrogens really close to one another. And then we have a couple of positions where those methyl groups can be as far apart, or pardon me, we have this position where the methyl groups can be anti to one another, as far apart from each other as possible. And so that's going to be, the highest, or pardon me, the lowest energy conformation. The gauche conformations are a little bit higher than that anti, and then we can also have eclipsing of the hydrogens and the methyls. So there's a lot of different possibilities here, and we can summarize them in this chart. So the eclipsing interactions, you can have hydrogen-hydrogen, like over here, that contributes 4 kilojoules per mole. You can have hydrogen-carbon, like over here, there's 2 of those in this molecule's conformation and this conformation. Methyl groups, when they eclipse, that's the highest in energy. And then the gauche interactions, where they're not eclipsing, they're actually staggered, but those methyl groups are still so sterically hindering each other or so close to each other that you do get an increase of energy over the anti. So, so this anti-conformation is the one that you're going to be finding the most of your molecules in most of the time because it is lowest in energy. And that is the staggered conformation. So the methyl group up here and the methyl group down here are anti to each other if you cite down this middle bond. So we usually draw the molecules as a zigzag because that is the lowest energy conformation. So when you see molecules drawn like this, note that that really is representing low energy molecules. So doing all this work with conformations, it's called conformational analysis, and it can really help us explain some things that would otherwise be really weird. Prion disease, why certain molecules react the way they do, why we find molecules in nature. We can do molecular modeling and understand better about how molecules actually look.